Thank you very much, Sarah Beth, and take it away.
All right, thank you, Chris. And yeah, feel free to interrupt with questions or clarification points. So yeah, that'll be great. Yeah, as Chris said, my name's Sara Beth Cebry. All the work I have done in this presentation, this was done at Cornell with Kian Sori-Hondo and Greg McCloskey. Yeah, so currently we are unable to predict earthquakes. Like that shouldn't be new information to anyone here, obviously, but kind of some of the reasons behind that, there are several reasons. Some is that the earth is really complex. So both what is like the current state of everything underground is really difficult. And it's also difficult to resolve the details of earthquakes that have happened through seismology. There's a lot of really great things we can do, but there's still a lot of questions out there. And also, models are typically simple relative to what is actually there. There are some really complex models. I'm not going to go into those, but we're also not sure if we have the right physics or models. So this is something at SSA like a month ago. Kayla Kroll kind of mentioned that induced seismicity is actually better predicted by statistical models than physical models, which I'm still thinking through a lot of why that. Like I'm still thinking a lot about that, but that really stuck out to me. And so, because we don't have all that information, we do rely on models. And so if we go way to the end to the simplest like model we can have of a frictional model, like even frictional models as well, we have a spring slider. And just to make sure everyone's on the same page here, spring slider, you have a block sitting on a plane, you pull the spring forward, it builds up shear stress on the block, and eventually you reach a peak. We're just doing really simple, like high school level friction here. And everything slips forward and the shear stress drops. So this is like that static and dynamic friction from high school. Again, we're just starting with like the simplest building block we can have. And this is not technically wrong yet, but there are lots of things going on. So, I mean, friction is way more complicated than this. I'm also not going to go too much into that. But using this as our earthquake model is that faults don't really behave as a single point. So we can add another layer of complexity. We can put all of these spring sliders in series. Say we're still keeping the same very simple static dynamic friction. All the blocks are the same. And that does get us a little bit closer to what a real fault might be. But as I kind of mentioned before, the earth is really complex. So we have different frictional material properties going on. Fault roughness also creates different stress distributions. There are things, and fault geometries also create a bunch of different like stress distributions and everything. And then the stuff that the anthropogenic side of things, where you get fluid injection, which also adds a bunch of different complexities. Excuse me. And we see that complexity come out when we look at things like natural variations and peak ground accelerations. So both like in 2023, the Turkey earthquakes and 2004 Parkfield, they're just really two clear examples where you have order of magnitude variations in peak ground acceleration. So how much shaking is felt at the surface. And there's a number of things that contribute to peak ground accelerations, but one of them is source characteristics that are affected by all of the complexity I mentioned before. So if we go back to kind of our mental building blocks of how we can look at like a spring slider model, all of a sudden our four very similar blocks may look something a little bit different. You might have frictionally weakening or very strong frictional properties on one. One block you can maybe think of as being way heavier than the other. It's like a higher normal stress. Or another one is also has different frictional properties. So there are lots of different ways to take this complexity into account when you're thinking about earthquakes or when you're modeling earthquakes or studying them. A lot of people go into some really great, really complex models, which are really cool and far beyond me. But I go to the lab. And so looking at the kind of thinking of these experiments a little bit more like a series of spring slider models, we can go to meter scale laboratory faults. So both of these are housed at Cornell University. They're both McClaskey style apparatuses. And so we can look at these large laboratory faults and then study how earthquakes can start, propagate, and as they run into complexities, or do the complexities affect propagation or termination or initiation, we can all do that. We can do that on these faults because the length of the fault is greater than the critical nucleation length. So I'm going to take a moment to kind of tell you why that's great. And what that allows for is that allows for contained dynamic ruptures. So if we have like the distance along the fault here and the stress state, say this P is your kind of like, if we're thinking about really simple spring sliders, that's your static stress state. This red line is your dynamic. And if you have a heterogeneous initial stress state, you can get a patch that is favorable for initiation and propagation, but if the ends are unfavorable for propagation, the event will terminate. And so that way you can get contained dynamic events. And if you have, say, you have a heterogeneity halfway down here, your event initiates where the stress is the highest. You can see how that complexity, lights turn off. You can see how that complexity affects your rupture and propagation. And this is one of the reasons, one of the questions that comes out of this is, how do earthquake ruptures stop? And this is kind of important for magnitude estimation. And one way that complexity can really start to play an effect on what earthquakes we see. So number one, your earthquake is going, it's propagating along fault, and it can propagate into unfavorable stress conditions. And so I have done some previous work on the 3-meter rock sample, as well as several other people, several other PhD students Greg has had. So that's one way. The earthquake is rupturing forward, and all of a sudden it kind of runs out of fuel. Or the opposite, the other direction can happen, where your propagating rupture enters a region of really high strength or high fracture energy. So this has been studied before, but I'm going to present some work today that has a bump, so a region of really high strength and fracture energy. That's kind of what my talk is going to focus on. And studying these from the lab perspective, this is again why you need the large laboratory faults, because you need to see the rupture stop after it's initiated, propagated, and then it has to terminate. So kind of a quick intro to these type of apparatuses. So this is 0.74 meter fault. This is PMMA. So we've got two blocks. We've got one, which we refer to as the stationary block. And so it's fixed on the top end, or the side and bottom. And then we have another block of PMMA, which we refer to as the moving block. And that's allowed to slip on this fault interface, as well as a low friction interface up here. So in our experiments, we apply a sample average normal stress to push the two sides of the blocks, to push the two blocks together. And then we apply a shear stress from the edge directly to the moving block. And that allows the low friction interface and the fault to slip forward as one unit, not to scale. And the fun thing about the lab is we can measure a ton of stuff, right? So we've got slip measurements. So those are eddy current displacement sensors on the top. And we also have digital image correlation. So we can get good spatial and good temporal resolution with these two methods. We've got piezoelectric sensors. So these are like our equivalent of ground motions. And in case anyone was curious what the inside of a panometrics sensor looked like, you've got your damping material and your backing mass and the piezo disc. And I just think that's a cool picture, so I always share it. And then we can also get strain measurements, either through strain gauges shown here, or again, through digital image correlation. And I'll talk a little bit more about these as I go through. And so that's kind of the overview of the apparatuses. And now I'm going to turn things around on you. So this is the same top-down view. And if we were to look at that model the way Kian and myself would be standing in front of the apparatus, you see the two blocks here. You see the moving block, which is shown in blue, the stationary block, which is shown in clear, and that's kind of the fault interface. And we're pushing on it from that side. So when we push on it and the entire block starts to slide forward, what happens is rupture will initiate kind of usually closest to the forcing end in these experiments, and then it just propagates smoothly along the entire fault. So because it's a compliant material and because we have the high temporal resolution on our slip sensors, we can see the propagation of the rupture along the fault. And so this is cool, and there's a lot of stuff that we can get out of this. But what I do in these experiments is I kind of try and create an isolated bump to be similar to a double restraining fault bend, right? So natural faults like this one in New Zealand have a lot of geometrical heterogeneity. And so if you have a fault bend here, it's kind of like cartoon version over here, as the two sides slide together, they're going to get pressed into a higher, going to get pressed into each other and have a region of high normal stress here. And so I kind of told you about the apparatus, but I didn't really tell you about the composite sample. And so if you're not really a lab person, you can kind of space out for this slide, but for the lab people who are interested, so we have these composite samples, which is opposed to one big chunk of PMMA or granite or whatever your lab material of choice is. There's a whole bunch of little blocks that are held together with tension rods. So, and then we have a support bar to make sure nothing buckles up in our face. And because they're not glued together, they're only held together. They're allowed to slide relative to each other. And so that's how we add a bump. So we have our composite sample here. Here's kind of the model version. And if we zoom in on a few of these subblocks, what we do is we add metal shims between the PMMA and the loading frame, and we only add them to one of the subblocks. So one of these subblocks, when we push the entire sample together, is being pushed a little bit harder than the ones around it. Such that on the fault, we see a bump in normal stress. So kind of like if anyone's familiar with like the Princess and the Pea fairy tale, where there's a pea at the bottom of a stack of mattresses and the princess can always feel the pea when she's asleep, the fault can feel the shims on the fault interface as a bump in normal stress. And now, of course, our blocks, they are being held together, and as they're being pushed together, the interfaces between the subblocks are not perfectly frictionless. So our bump is not just one subblock, it actually kind of spreads out to a little bit of the others. And the cool thing we can do in the lab is that we can measure this. So using digital image correlation, there's a lot in this picture, but there's also that picture's in a paper if you're interested in that. But by looking at a reference box looking at the digital image correlation speckles that we have painted on our block, we can tell where they move. And so between one image and the next. So we can start when there's no stress on the fault and then increase it a little bit and increase it a little bit and see how the stress state along the entire fault changes as we increase normal stress, as well as throughout the experiment. And so what we see is that we see right where the shims are being applied here, we have a very prominent, very high bump of normal stress. So that's always cool to be able to, and it roughly matches just like elastic measurements as well, like a Hooke's law deformation measurement.
Sarah, sorry,
yeah.
Chris. How big are the blocks? Each block is a couple millimeters thick?
Yeah. Each block is 1 inch, so 2.5 centimeters.
Gotcha.
Yep.
Yeah, so because your measurements are showing sub-block resolution, like so the block itself has a high point in the stress, and then at the edge of the block, the stress is a little lower.
Yes, and that is true. And so because all of the sub-blocks are just tied together, they can slip a little bit between them. So you do get some rotation of the blocks. So even within each of the sub-blocks, there is a little bit of stress variation as well.
Gotcha, thanks.
So when we add the bump, so here we have the continuous, right? We talked about it initiated on one side and propagated smoothly. When we add a really large bump to the fault, it starts to change the behavior a little bit. So we get some events where it initiates on one side of the fault, propagates, hits the bump, and does not slip, and then reinitiates on the other side of the bump. So in this one, the bump is locked the entire time, but the rest of the fault has slipped. And we refer to these as kind of partial events. We also, you could have one event like that, and the very next event in the sequence, so all we're doing is continually loading shear stress, it'll behave even differently. So it starts off similar, initiates on one end of the fault, propagates to the bump does not rupture, it remains locked. Rupture reinitiates on the other side of the fault. So the entire fault has slipped at this point, and then rupture comes back, the bump slips, and then repropagates and re-ruptures the rest of the fault. So we have a lot of different kind of events that we can see just by adding a bump. And these events can happen all within the same sequence. So you might get several events where the bump doesn't slip, and then one event will slip the bump. As opposed to when we don't have a bump, we never see that sort of behavior. All of the events are very, very similar. And so what we can do is we go through and we systematically vary the number of shims applied before the experiment, and as well as the normal stress. And what we found that was increasing the bump stress. So the more shims we put in, the higher the stress on the bump is here. So here, if this is normal stress along the fault, you have your bump, and this is the bump stress. So how high, it's like the prominence, how high the stress is above the sample average normal stress. And so as we increase the number of shims, we go from that continuous events like I showed a while back, where each event is the exact same size as the one before it, to variable sequences where you get some events like this small one here that only slip part of the fault, and then you'll have large events which slip the entire fault, including the bump. And then the opposite happens that also happens as we decrease normal stress. So for the same, in this case, I'm showing everything has 6 shims. So the stress on the bump is the same, or the bump prominence is the same over the background stress. And at 8 MPa sample average stress, so when we're pushing both of the blocks together at 8 MPa, you get very repeatable continuous events. Whereas if you're only pushing the blocks together at 2 MPa for the same size bump, you get these variable complex sequences as well. So to understand kind of why this is, we look at individual sequences to learn a little bit more about all the different mechanics that are happening. So here we have the average slip from 1 down here. This is kind of the most consistent sequence. And then we also take the most complex sequence. So they're both at 2 MPa, one with a lot of shims and a very high stress on the bump, and then one without. And so looking at the really complex one, I'm going to go into a little bit more detail about all the different events that are happening. So we see these complex sequences where you have one really large event, and then small ones, and then a medium-sized one, and a small one, and then a slightly larger one. So the really small events, we can look at the slip distribution. So this is the distance along the fault. And then up here, we have the apparent slip. So the amount of slip measured by our displacement sensors. And so the slip measured at 8 locations along the fault. So we have one event, where it just slips a small portion of the fault and then terminates both at the bump right here and at the front edge. We then have another type of event where it begins similar to the first one, propagates, kind of pauses for a minute, and then continues to propagate, but doesn't slip, only slips about half the fault and doesn't slip the bump. and this is, I'm going to make a kind of clarifying point actually with this next one. This is slip measured at 8 locations along the fault and are with very sensitive slip sensors. So it actually can measure a little bit of changes in shear stress due to the compliance of the PMMA. And if you're a lab person, I can talk to you more about that if you're interested. But understand that, and then I'll get into a minute, but the digital image correlation, we can actually resolve and confirm that the bump is not slipping. I'll prove it to you in a minute, but you'll have to take my word for it for now. Yes, so we have small events, medium events, slightly larger events, where that starts off looking like a small event, and then kind of one of the medium events before propagating even further along the fault. But in this case, the bump still remains locked. Finally, we have our large bump rupturing events that, again, these all kind of start similar. So it starts similar to a small event. We can see that it propagates onto x equals 0, so that's where the forcing end is. We see that it pauses very similar to this type 3 event or a kind of a larger event before rupturing the bump and re-rupturing the entire fault. So to confirm that the bump isn't slipping, we go into the use digital image correlation to measure points really, really close to the fault and have really good spatial resolution. And we can look at different events. So we take a picture before the event and a picture after. These are like static measurements. We don't really have great temporal resolution with the digital image correlation camera we have. I know there are a lot of people that do some really cool stuff with that. I know like Aries Versakis has really good dynamic measurements with digital image correlation. These are just static, so a lot simpler. And so this is me proving to you that the bump does not slip. So I showed you some of the stuff before, and what you can see here is that, so here I highlighted where the bump is. You can see it. We have slip events that slip one side of the fault. I kind of like colored this one purple here. It's nice and easy to see. So it slips one side, doesn't slip the bump, and then slips the other side here. And then when the bump ruptures, it actually relieves all of that slip deficit that's kind of been built up. And so we have our large bump type 4 event. I can see that it slips to a mostly, the fault at that point had all slipped pretty uniformly. And again, with the bump slipping more than the rest of the fault. The other thing we can do with digital image correlation is we can get some sense of the stress measurements. So we can't see in this experiment what the stress is outside of the bump. It's too noisy and it's not above the resolution, which is about half an MPa. So the stress changes out here are very small, but we can see that the stress changes on the bump are very high. So this is the before and after this large event here. So we see a large stress drop on the fault, and we see a non-measurable, so less than half an MPa stress drop off the bump. And so all of this is to kind of bring about the question, what controls if a rupture terminates at the bump? Because we have experiments that even though they have a bump, so you say you have a really high normal stress, and then not a huge bump, but even if you do have a bump, the bump may not be large enough to terminate rupture. So we're trying to ask what controls if rupture terminates at a bump. So in these really variable sequences, why does it sometimes terminate at the bump, but not other times? And so there are kind of like 3 factors that control whether or not the bump ruptures. So we have bump strength, we have the stress increase from the incoming rupture, as well as stress already on the fault. And if you like to think in energy, these have a lot of energy comparisons. You can think of like a high fracture energy, the delta tau potential, the potential energy you have, as well as like the energy at the crack tip. And some of these aren't new. We're pretty familiar with the stress already on the bump relative to the strength. We have a term for that. We have that, it's called strength excess, if you're familiar with that term. And we can also look at what changes during an experiment and what doesn't. So the bump strength is consistent throughout the entire sequence, right? that depends on the number of shims we put in at the beginning of the experiment, and that doesn't change throughout the experiment. Nor does the stress increase from the incoming rupture really change. It'll change between some of the types of events, but like our type 1, the really small one, that stress change isn't going to change during the experiment. It'll change based on the rupture size, but that will stay consistent. And that depends on the normal stress, the sample average, so how hard we're pushing those two blocks together. And then thirdly, we have the stress already on the bump. And so this is the only thing that's going to change throughout the experimental run, right? I showed you with the digital image correlations, the stress measurements. We can see that each of those small ruptures, so each rupture that doesn't slip the bump, kind of adds a little bit of shear stress to the bump. It keeps building up the stress on the bump. And so we go through and we characterize all of the different experiments we've done at different normal stresses and different number of shims. And we call this the bump prominence. So how high the bump is relative to the rest of the fault. And if we plot everything out, all the experiments we did on a map, and kind of color code it by the variation of the events. So our highly variable events, you have a lot of variation. You have big events and small events. Whereas these consistent ones, all the events are the same size because the bump doesn't stop rupture. So that's probably a simpler way to think of it. You can think of the ones down here, the bump never stops rupture in our experiments, or the duration of our experiments, whereas these variable ones, the bump sometimes stops rupture. And what we found is that it's kind of well characterized by the bump prominence. Again, this bump stress over background stress. And we found that that's about equal to 6. And this all matches different models and experiments. So Sudhir in 2024, who had some really great models that showed also this similar value of about 6, kind of makes sense for whether or not a bump can stop rupture. We also, if we go even further back in time, we can see that like Das and Aki had some very similar models. They also showed that bumps can stop rupture, and they can show that rupture can actually bypass a bump, similar to what we are seeing in a similar kind of slips one side of the fault and then slips the other type pattern. And there are also other experiments looking at heterogeneous fault stress states that show basically how important they are, and that how you can how that controls a lot of where a fault slips. So kind of some of the main takeaways looking at the mechanics of whether or not of the effect of a normal stress bump. What we see is it's not just how big the bump is, but how big it is relative to everything around it. And we kind of term that the bump prominence. And that has a big effect on whether or not the bump will be able to stop rupture or how it will control everything. We also saw in these really variable sequences that a bump can act as an asperity or a barrier. So there are several events where the rupture comes in and terminates at the bump. So the bump is acting as a barrier, not letting rupture through. But then there are other cases where the bump actually acts as an asperity, and all of that built up energy goes and re-ruptures the entire fault, resulting in a larger event than would have otherwise happened without a bump. So when we talk about the variable sequences, that's kind of the origin of the complexity of these sequences. And this is really similar to the earthquake gate concept from Oskin in 2025, where you have a rupture that comes in and it terminates, and then another one terminates, and then finally the gate opens and rupture can propagate along the entire fault. So this kind of concept has been seen in nature as well. The other takeaway that we had is the bump could never stop rupture permanently. So you could see a bump stop several events, one after the other, but eventually that gate opened and the bump slipped and created a really large event. So now we also kind of get into some of the questions about, well, why do we really care? Rupture dynamics are really cool, but that's not like I have a civil engineering background, so sometimes we need to understand how those earthquakes are going to affect us. And so we looked at peak ground acceleration of these complicated events with a bump. And so a little bit on peak ground acceleration. There are several things that affect peak ground acceleration. You've got path effects, soil effects, and source effects, to name a few. But this parameter is really important because when you have an earthquake, what actually damages a lot of the buildings are the high frequencies. And so peak ground acceleration is a standard parameter that is used to design infrastructure as well. So I kind of pulled out this ASCE, is the American Society of Civil Engineers. And in the US, a lot of the parameters that they put out are what is used to design buildings. So if you're in the US, you are probably sitting in a building that has been designed based on ASCE standards. And this is just a hazard tool that shows I just moved to the San Francisco Bay Area, so I can go and look at what the PGA building standards are for my location. We're here at Moffett Field. And that was used to design probably the building I'm sitting in now. And so this also ties back into the fact that natural events have order of magnitude variations in PGA. So it makes it very hard to determine what kind of design standards and what your buildings and infrastructure should be prepared to withstand. And so in these experiments, we can measure ground motions through the piezoelectric sensors at 8 different locations along the fault. And our fault length, just kind of give you the sense of the spacing, our fault length is 740 millimeters. The max sensor spacing we have between the two is 120. So we have some pretty good spatial resolution along the fault. And what I'm going to look at, we're going to look at PGA, but because all of the distances from the fault to the sensor are both very, very close. So we're looking at near field peak ground acceleration, and B, it's all the same. So our path effects are all the same, and our site effects are all the same. They were all attached, all of the sensors were attached in the same manner, same distance from the fault. So I'm going to turn things on you all again and show you so we can see our ground motion measurements as a distance along the fault. So 0 is the forcing end, so that's where we're pushing one block past the other. We can see that rupture initiates on one side and propagates forward. So these are just the raw data from a single event. And we can process that data some. We can remove the instrument apparatus response. And so we can just look at the source amplitude here in the frequency domain. And so we have these 3 types of events that I showed at the beginning. So we have a continuous event. So this is one without a bump, this green one. And then we have partial events. So that's an event with a really big bump where the bump didn't slip. And then we have complex events, which are those where it slipped the entire fault and then the bump slipped and re-ruptured the entire fault. And what we see is that when you have a large bump, so in the case of the partial and the complex, it actually enhances the high frequency radiation. So kind of using this complex one as a comparison, at the low frequencies, which I'll highlight here, it's relatively similar to the complex one, the continuous one, I'm sorry. But in the high frequencies, and over here as well, we can see that the complex one, so when you had a really big bump, you have enhanced high frequencies. So to be able to compare, give you actually a good comparison, as well as compare between different experiments at different normal stresses and different bump prominences, we take an average of high frequencies and low frequencies that I highlighted here in those frequency bins. And then we can do the high frequency relative to the low frequency, like a spectral ratio. And so what that kind of gets at is a little bit of how much of these high frequencies, how much like the PGA or the high frequencies that damage infrastructure are there for the low frequencies, which are used to determine magnitude. So like for the same low frequency, so a little bit of thinking as the same magnitude, how much high frequency or how much damaging radiation will there be? And so what we see is as the bump prominence increases, both the kind of the maximum of this value and as well as the average of this value increases. And what's kind of interesting to look at, so I'm highlighting that 6, that when the bump prominence equals 6, that we found from kind of looking at the mechanical side of things, as well as has been shown in other models, that beneath it, so below this 6, this dashed blue line, the ruptures are relatively continuous. The bump is not able to stop rupture, whereas above it, the bump is able to stop rupture. And we kind of see that as a nice marking between pretty low high frequency to low frequency and very high and variable high frequency to low frequency amplitude. And again, this is expected. There have been several modeling studies that have shown this. I'm just kind of listing a few, but particularly this Dasanaki in 1977, they showed, so the dashed line is without a bump, the solid line is with a bump, and they showed that having a bump increases these high frequency radiation. And this can make a bit of sense relative to natural faults as well. So their study of, this is kind of looking at induced seismicity in Guthrie, Oklahoma. And what they found is that you kind of had this segmented multi-part rupture, and that showed up a lot in the frequency. They were able to see that in the frequency domain. So kind of the deviation from like a Brune model, and it was had directional effects as well, but just kind of looking at this forward direction, you have enhanced high frequencies and some enhanced in some frequency bands, and it's a little bit more depleted in others. And the study kind of pointed out that this had a lot to do with the multi-segment rupture effect. So like where one portion of the fault slipped on the next in the back, which was kind of cool to see it on a natural scale as well as being able to see it on the lab scale. But one thing that's really cool we can do in the lab is we can look at the spatial heterogeneity of this high frequency energy. So where is the radiated high frequencies coming from relative to where the rupture is along the fault? And so what I'm showing here, we have distance along the fault here. So again, we're looking along the fault. Rupture is propagating from this forcing end along the fault. And I'm showing both high frequency energy. So the piezoelectric data is high pass filtered to the point where for one piezo sensor, it's really only measuring the energy radiated closest. You're only measuring, as the rupture front propagates, you only see the high frequency energy at the sensor closest to the fault. So yeah. And then also in black lines here, we have the slip data measured from the eddy current displacement sensors. So in the continuous case where there's no bump, rupture initiates closest to the forcing end and kind of propagates forward. It propagates at a continuously and smoothly, and it also propagates super shear. So we have our P and S wave speeds here, and this is, so I'm saying super shear, and this is not unexpected for a plexiglass sample in the lab. It's a planar fault. This is pretty reasonable to expect super shear. Yep, so we have one main rupture front coming through, and then we have a few smaller re-rupturing the fault kind of as the rupture propagates back a little bit. So that's the continuous case. And then now we have the complex case where we have the bump added in here. And kind of as we mentioned, we went over this a lot in the mechanical side of things. Rupture initiates a little bit more towards the middle of the fault, propagates outward. We see that the rupture re-initiates and propagates beyond the bump. And then finally, in green here, we see that the bump slips, and that creates a really large, that emits a really large burst of high frequency energy. So I kind of showed you the peak of the green here and here, and you can just compare that to basically anything else on this plot and see that it is much larger. There's much more high frequency energy being released when that bump slips than anywhere else on the fault. and even anywhere else on the fault on the continuous case. It is also worth noting on this complex one, nothing on the complex, the rupture does not hit super shear in the complex case. So all of this is sub-shear speed. So we can also convert, so we see that there are a lot of enhanced high frequencies. But what does that actually mean? We convert it to peak ground acceleration to kind of to get a more meaningful result that we can compare. And so to determine the peak ground accelerations, we took the raw spectra in a certain frequency range when we were able to convert where the frequency response of the sensors is flat. And so we're able to convert directly to displacement measurements. And then we were able to convert displacement to acceleration. And so what we see is that in the continuous case, which I have here on the left, peak ground acceleration kind of matches what we expected from looking at just simply a high pass filtered raw data. And then we see it's mostly continuous along the entire fault. There's some variation, but it's all pretty small. Whereas in the complex case, we see that it's relatively similar outside the bump, but on the bump, the high frequency, the peak ground acceleration is much higher. It's about 6 times higher than anywhere else on the fault. So that's really cool that we can see that a prominent bump produced more peak ground accelerations, despite the fact that this event never reached super shear than a continuous event that was propagating at super shear speeds. So source parameters definitely have a large effect here. And the other thing, if we go back to this digital image correlation that I showed earlier, where we see that we're looking at basically this purple event here that I colored in, as well as the stress drop here. So here's our peak ground acceleration, correlates with the bump, and that also correlates with a larger change in shear stress, like local parameters as well. So we see that there's a large stress drop, and when I say stress drop, I mean change in shear stress from before the event to after the event. We see that there's much higher slip on that section of the fault, and I don't show it on this slide, but there's also a large change in peak slip rate. So it's cool to see the kind of connection between those source parameters as well as the enhanced peak ground acceleration. So we can draw a comparison between what we're seeing in the lab and the 2023 Turkey earthquakes. And so after those earthquakes happened, there have been a whole lot of publications about it, which has been really great. So we can look at and see that those earthquakes, they had complex rupture patterns. So if we look at this paper from Gia et al., we see that there's a lot of different timing variations. So they have the different colored dots are showing the different timings and events. You can see it in this way as well. There's some probable geometric barriers going on. And again, you can kind of see it either in this plan view map where there are a lot of different fault segments, there's a lot of different intersections. And then all of this produces a pretty high variable peak ground acceleration. So you can see the variations. Sorry, that text is a little bit small. But the red zones here have a very high PGA, whereas further out in the yellow, it's even lower. And so they've also kind of come to the fact that geometrical heterogeneities might be a plausible explanation for the natural observations in near fault peak ground accelerations. And so what that kind of brings up is I kind of use this graphic to illustrate kind of the questions this brings up. So in a laboratory fault, we have no bump, normal stress is homogeneous, peak ground acceleration is relatively homogeneous. When we add a bump, so we have a big bump in the normal stress in this black line, we see a corresponding variation in peak ground acceleration, both in the average, which is where the triangle is, as well as the maximum and the minimum indicated by the lines. So what does that mean for natural faults where we have large variations in normal stress and we see large variations in peak ground acceleration? But it's not always easy to predict. So that's kind of the open-ended question I'm going to leave with. It's kind of some key points from looking at the frequency effects of having a large normal stress bump. is that the complex ruptures, due to a bump, have a much radiate more high frequency energy, and that high frequency energy is spatially heterogeneous. They also see that smooth continuous ruptures don't really match natural observations of peak ground acceleration. The complex normal stress kind of adds another layer of complexity, which matches a little bit better to natural faults. Kind of overall conclusions from my talk is we see that fault heterogeneities promote variable event sequences with repeating large and small events. So this is really important for understanding earthquake mechanics and understanding how faults behave, span on natural scale as well as the lab scale. We see that stress levels played a really critical role in determining when ruptures stop. And this is important for magnitude estimation. So knowing when the rupture is going to stop will determine how big it is, and so allow for better magnitude estimation. And finally, we see that complex ruptures can produce more high-frequency ground motion than smooth ruptures. And this is important for hazard prediction, considering that our peak ground accelerations are a major design implement. And so understanding the damage these events can produce is really important for predicting hazards and keeping everyone safe. And that's all. Thank you.
Thank you very much, Sarah Beth. What an interesting talk. I'll invite people to unmute, join me in thanking Sarah Beth for a great talk. Yay, or
Thank you.
Yeah, use your reaction buttons. Yeah, what a lot of interesting things. So I will invite people to use the reaction button at the bottom of your screen, and we can put ourselves in order to ask questions and things. And a few weeks ago, I started a plan we'll record for a few minutes of questions and answers for posterity, let's say, and then I'm going to shut off the recording. So if that's easier for some people to ask a question. Yeah. So thank you very much, John Vidal and Paul Johnson, for showing us how to do it. And I do want to encourage everyone on this call to join into the conversation. Raise your hand and ask a question. John, please go ahead.
Oh, okay. I just had a couple, but just to start, when you say super shear, maybe you go back to slide 45 or 46, because it looks like on the left, the rupture doesn't seem to start until like the S wave. The black curve doesn't really move with that initial vibration. It looks like it comes somewhat later, closer to the slope of the S wave. So it's not the P wave?
So this is high pass filtered.
Right, but the black curve is not, right?
The black curve is not. The black curve is the slip measurement. And so that's coming a little bit later. So yes, there is some effect because the piezo sensors measure it before the slip sensors.
Right, but super shear would refer to when the fault displaced, right? So it looks, the black curve seems to parallel the S velocity. You see what I mean?
Are you calling the S wave here?
Well, I can't really draw on it, but it just,
Yeah.
at 60 centimeters, the black curve doesn't really move till, I don't know, a little bit after the initial wave. Anyway,
Okay.
It seems like the rupture velocity would be when the black curve moved, not when the initial vibration showed up.
Yeah, but it's a constant delay between them all.
Okay,
well.
anyway. So, all right, that was my question. I'll come back later with another if people run out of questions.
Sounds good, John. Thanks very much. And I raised my hand only to encourage people to continue joining the discussion. There's lots of people, so let's go ahead. Paul Johnson, please.
Thanks, Chris. Thanks, Sarah Beth. A really interesting talk. I feel like I learned quite a bit about the heterogeneity and in geometry of the fault and its effect on the spectrum. And that was enlightening for me, for sure. I just had one kind of technical question. Is it possible there's differential slip along each segment perpendicular to the fault that could be contributing to the overall behavior of the fault? Have you thought about that and what the effect might be?
You mean like between these?
Between each segment, perpendicular to the fault. I realize they're held in place by individual stress sensors,
Yep.
but I'm wondering if there could be differential slip.
There is a little bit of differential slip going on. What it mostly happens is, so we have a run-in phase in these experiments where as we're loading it up, that slip between the interfaces has a huge effect. It sounds like you can hear it on all these little subfaults making a bunch of little crackling noises, and then it kind of settles in. So it kind of reaches a constant steady state behavior. So all of these experiments are done after a lot of that slip between the interfaces has already happened. So I think it has a relatively small effect. And also the slip on the interfaces is much smaller than on the fault. So relative to what is actually happening on the main fault, the effect of the slip on these subfaults is pretty low.
Yeah, and I guess clearly at lower applied loads, the effect could be larger. So become progressively larger the lower load you apply, I presume. And I don't know if you would agree with that or not.
I would disagree with that because as you increase the stress, as you increase the load, you're going to have to increase how much load is being applied. Both here as well as here. So I think it'll be proportional regardless.
Okay. All right. Well, thanks, Sarah. That was the question. Thank you very much for enlightening talk.
Thank you.
Thanks, Sarah. Yep, Garrett Drazen, please go ahead.
Yeah, Sarah, very nice talk. Thank you very much. I actually had the same question as Paul had, but on top of that, I would also ask, does the width of the bump change depending on how many shins you put in?
The width of the bump does not change based on the number of shims because all of our shims are the same size.
Okay, I thought just by affecting the neighboring blocks, when you put more load on a single block in some way, then it will expand. And
yeah, it only really affects the block next to it.
Yeah, okay.
It doesn't really go beyond that.
All right. So and the other question I had was, you presumably had some pre-slip occurring, right? Which you didn't show here. And that certainly was also affected by the presence of the bump, right?
This is PMMA, so there really is not much pre-slip in terms of like a nucleation patch. I mean, it's there, but our sensor spacing is larger than the critical nucleation length, so we can't really see it or characterize it very well.
Okay, thank you.
And as we go to Chaz Bolton, I will encourage people to join the discussion. Chaz, go ahead.
Hey, Sarah Beth, really nice talk. I just had a quick question on so the example that you show where you have this bump, right? And then first it sort of acts as a barrier to rupture, so it terminates. And then you say the next event, the event nucleates right at the barrier. Is that correct?
It always nucleates in the same location, whether or not it slips the bump or it terminates at the bump. So it always initiates right about here, which is where the normal stress is lowest relative to the shear stress. So it always initiates about here. Sometimes it propagates and terminates at the bump. Sometimes it propagates and then slips the bump.
Gotcha. And then so does that process repeat? Like after it sort of terminates at the bump and then the next one, it sort of happens on the other side, or I guess it propagates through it. And then does that cycle kind of repeat continuously as you go throughout the experiment?
Yeah, so we definitely see super cycles where you'll have a large event and then smaller and medium-sized ones and then another large event. But the pattern of small and medium size is not always the same.
Gotcha.
There are a few little rules you can kind of see, like there's always the smallest one before the largest one, but there's no like ABC, ABC, ABC pattern.
Yeah. And then another quick question is, in some of the work that Greg's presented in the past, and I think